In this lecture, I'm going to define covectors and introduce the metric. Now let me remind you that a vector, in the context of curved space or space-time, we have to define as a directional derivative operator. So a vector, or more precisely a contravariant vector, is a derivative operator. Right, so mathematically speaking, a vector is an object that maps functions to numbers. All right, so given a function, a vector will map it to a number. Now, let me point out that we often work with vector fields, meaning a field of vectors, a vector defined at each point in the space. And in that case, the vector at each point will map a function to a number. So you could say that a vector field maps functions to functions. But a single individual vector that sits at one point will map a function in the neighborhood of that point to a number. If our coordinates are denoted xi, then we can always expand any vector as a linear combination of these basis vectors. The basis vectors are the derivative operators in the direction of the coordinate lines. And let me remind you, I'm using the Einstein summation convention here. So anytime you have a repeated index, like the index I, that means there's an implied sum over I in this expression. All right, let's take an example. And I'm thinking in the context of just flat two-dimensional space with Cartesian coordinates. So the line element is dx squared plus dy squared. And let's consider the vector v equals y squared d by dx minus 2x d by dy. And let's take the function to be xy plus x. And we'll consider this at the point P given by x comma y equals 1 comma 2. So you'll notice what I've defined here is really a vector field. It's defined at each point in the space. But we'll just consider the vector that sits at the point 1 comma 2 and let it act on this function. All right, so the vector at the point P is setting y equal 2, we have 4 d by dx minus 2 times 1, that's 2 d by dy. So that's the vector that sits at this point, 1 comma 2. Now let this vector act on the function f. It's called the vector at that point v sub p. Acting on the function f is 4 d by dx minus 2 d by dy, acting on xy plus x at the point P. So this is 4 times the derivative of the function with respect to x is y plus 1, minus 2 times the derivative with respect to y, which is x, all evaluated at the point P. All right, if we insert y equal 2, this is 4 times 3 is 12. Inserting x equal 1, we have minus 2, and we have our answer is 10. Right? So when this vector at this point acts on the function given, it gives us a number, the number 10. Now let me define covectors. A covector is also sometimes called a covariant vector. Sometimes called a dual vector. And in some contexts, it's also called a one-form. But I'll just refer to it as a covector. How is it defined? Well, let me first repeat our definition of a vector. A vector is an operator that maps a function to a number A covector is an operator that maps a vector to a number. Let me give you an example of a covector. All right, given a function, say call it phi, then d phi is a covector. Now this symbol d is sometimes referred to as the differential. This would be the differential of phi, or sometimes called the exterior derivative. Now this symbol d is a symbol that we've used a lot already in this course, and we've always interpreted it intuitively as meaning a small change in the quantity. So d phi would be a small change in phi. So I'll discuss later on the connection between this intuitive notion of d phi as a small change in phi and the interpretation of d phi as a covector. In other words, as an operator that acts on vectors to give numbers. So how does d phi act on a vector to give a number? Well, d phi acting on the vector v is, in this case, it's just the number that you get when you let v act on the function phi. All right, so this is a number. So this is the covector acting on a vector to give a number. Let me point out that we can always expand d phi using the chain rule. So this would be partial phi with respect to xi dxi. And remember, I'm using the Einstein summation convention. So this repeated index I means I'm summing over I. Now we can view these coordinates xi as functions on the space or space-time. So this is the exterior derivative of those functions. So these quantities are referred to as the basis covectors. Right, they're the exterior derivative of these functions xi. And then the coefficients are then the components of this covector in this basis. In this basis. So d phi is a particular type of covector in that it's constructed as the exterior derivative of a function. But in general, we can write any covector as an expansion in terms of the basis covectors. So if w is my covector, we can always write it as an expansion of the form wi dxi. So the wi are the components of w. Notice that I've written the index on wi as a subscript, and that will always be the case for covectors. We always write for the components of a covector, the index is always a subscript. Whereas for a contravariant vector, the index is always a superscript. All right, now one thing I really should point out here is that this is a general covector. Whenever we have the differential of a function, that's a particular type of covector, and not every covector can be written as the differential of a function. So for example, let's take the covector y dx plus x squared dy. Can this be written as d phi? Well, if so, then this would be partial phi with respect to x dx plus partial phi with respect to y dy, just using the chain rule. So it must be that comparing these two expressions, we have partial phi with respect to x equals y, and partial phi with respect to y equals the coefficient of dy here, which is x squared. So the question is there any function that has these properties? And the answer is no. One way you can convince yourself that that's true is by differentiating this equation with respect to y. So we would have second partial of phi with respect to y and x is equal to 1. But if we differentiate this expression with respect to x, we have the second derivative of phi with respect to x and y is equal to 2x. So now these must be the same for any suitably nice function phi. So the fact that these are different tell us that there is no function phi that has the property that d phi is w. Let's look at a specific example of a covector acting on a vector to give a number. So let's take the covector that's built from the function phi equals x times sine y. And then our covector will be d phi, the differential of phi, that's sine y dx minus plus x cosine y dy. And let's let this covector act on a vector, the same vector we used before, y squared d by dx minus 2x d by dy. And consider the point P defined by x comma y equals 1 comma 2. All right, at this point, the covector at the point P is sine of 2 dx plus 1 times cosine 2 dy, and the vector it's going to act on at that point is just y squared is 4 d by dx minus 2 times 1 is 2 d by dy. All right, so d phi at that point P acting on V at that point, this is all at the point P. Well, remember that whenever the covector is of the form, the differential of a function, this number is the same as the number that we get by letting V act on the function phi. All right, so that's, take this vector V, that's 4 d by dx minus 2 d by dy. Let that act on the function phi that we started with, that's x sine y. And this is all at the point P. Okay, simplifying this, we have 4 times the derivative of the function with respect to x is just sine of y, minus 2, the derivative is x cosine y. That's all at the point P. So that's equal to 4 sine of 2 minus 2 times 1 cosine of 2. Okay, so here's the number that we get when we let that covector act on the vector. Now let's, we'll come back and evaluate this in another way, but let me first take a closer look at the basis covectors and basis vectors. So the basis covectors are the dxi's, and x is a function on space. So again, this is the exterior derivative of x, I, for each value of I. So how do these act on the basis vectors? The d by dxi's. All right, well, let's just compute. Let's take dx acting on partial with respect to x. All right? This is the exterior derivative of x, so this covector acting on this vector is the same as this vector acting on this function, which is of course 1. We can compute the covector dx acting on the vector d by dy. That's the same as the derivative of x with respect to y, which is 0, and so forth. dy acting on d by dx is the same as the derivative of y with respect to x, which is 0. And finally, dy acting on d by dy is going to give 1. So in general, whenever we have a basis covector acting on a basis vector, okay, and now notice I've used a different index here and here. I used I here and j here. I don't want to use the same index because that would be a repeated index, which would imply that there's a sum over that index. In this case, I don't want to sum over the index. I want to consider one particular dxi acting on another particular d by dxj. Okay, and the values of I and j can be independent. All right, so this is just partial xi with respect to xj, which is either 0 or 1, depending on whether I and j are the same or not. So this is actually the Kronecker delta ij. It's 0 if I and j are different. It's 1 if I and j are the same. All right, so given this result, we can now go back and evaluate this covector acting on this vector directly. All right, we have the covector d phi is sine y dx plus x cosine y dy, and the vector was y squared d by dx minus 2x d by dy. So now d phi acting on v is, let's just go ahead and write this out. This is y squared d by dx minus 2x d by dy. All right, so dx is a covector acting on this basis vector, just gives 1. So that's y squared times sine of y. When dx acts on d by dy, it gives 0. dy acting on d by dx gives 0. And finally, dy acting on d by dy gives 1. So that's minus 2x times x. That's minus 2x squared times cosine y. Okay, the way I've written it here, it's really a covector field acting on a vector field. So it actually gives us one number for every point in the space. But if we want to evaluate this at our point P, which was 1, 2, that's y squared, it would be 4 times sine of y, that's sine of 2, minus 2 times 1 squared is 2 times cosine of 2. So here's our answer, and it should be the same if we check here. Yes, it's the same. So let's switch to our notation that's common for space-times, in which we let the coordinates be denoted x mu. And a general vector or contravariant vector can be expressed as a linear combination of basis vectors, the d by dx mu's, and a general covector can be written as a linear combination of basis covectors dx mu. And notice I've written the index on the components of the vector as superscript, the index on the components of the covector are written as a subscript. All right, now let's let this vector act on this, or rather this covector act on this vector. All right, what do we have? We have w mu dx mu, this covector, acting on the vector v nu d by dx nu. Now, let me remind you, we're using the Einstein summation convention. That means in this expression, we're summing over mu. Also here, we're summing over mu because it's a repeated index. Here, we're summing over mu, and we're also summing over the index nu. Now, the reason I changed the index on the components of v from mu to nu is because I didn't want these indices to be confused with these indices. Right? These are separate sums. This is really the sum over mu of w mu dx mu. That covector acts on this vector, the sum over nu, v nu, d by dx nu. Right? So, in particular, this is not equal to the sum over mu of w mu dx mu acting on v mu d by dx mu. All right? And in fact, you'll never see an expression like this written in relativity. A properly written expression can have repeated index, which means there's a sum, but the repeated indices should always occur in pairs. Okay. Repeated indices always occur in pairs. In other words, just two at a time, never four like in this expression. All right, so now continuing, we're considering just a general covector acting on a vector v, and we can express it in this way. Now, we know that, and let me, again, Einstein summation convention, I won't write the summation symbols. So going back to this expression, we have w mu v nu dx mu acting on d by dx nu. Now we know how a basis covector acts on a basis vector. This is just the Kronecker delta mu nu. So in other words, it's 0 if mu and nu are different. It's 1 if mu and nu are the same. Okay, so this is equal to w mu v nu delta nu mu. And now, if we look at, say, this part of the expression, we have a repeated index nu, which means nu is being summed over, but all of the terms in the sum are 0 unless nu happens to equal whatever the value of mu is. So v nu delta nu mu is just v mu. All right, so our result here is that w acting on v is w mu v mu. This is an important result. What we have on the left-hand side here is a rather abstract construction. It's an operator acting on a vector to give a number, but this shows that we can compute it quite easily in terms of coordinates. We just simply take the components of w in a coordinate basis and wire them together with the components of v in the coordinate basis. And by wiring together the components, I mean making the indices the same so that by the Einstein summation convention they're being summed over. Now that we have a basic understanding of covectors, let's return to this question of the meaning of the symbol d. This is the differential or exterior derivative. But we also often interpret it as a small change in something. Okay, how do we relate these points of view? So let's, in particular, let's look at the exterior derivatives of the coordinate functions. These are the basis covectors. All right, in what sense is this the same thing as a small change in x? All right, now just to be clear in this discussion, let me write, whenever I'm thinking in terms of a small change in x, let me write that as delta x mu rather than dx mu. And whenever I write the d, I mean it in the mathematical sense as the differential or exterior derivative. All right, well, what do we mean by a small change in the coordinates? Well, let's draw a picture here. Let's say we have 2 points in our space that are close by. And now we can draw a curve that passes through those points. And let's let that curve be parameterized by some parameter lambda. So this is the curve x mu of lambda. And it passes through our 2 points. And we'll let this point have parameter value lambda 0, and this point have, since it's nearby, it has a parameter value that's close to lambda 0. We'll call it lambda 0 plus delta lambda 0. Okay, with the, again, the symbol big delta just means a small change in lambda. All right, so the coordinates of this point are x mu of lambda 0, and the coordinates of this point are x mu of lambda 0 plus delta lambda. All right, now, since delta lambda is small, we can expand this in a Taylor series. This is delta mu of x0 plus delta lambda times partial x mu with respect to lambda, evaluated at lambda 0. And of course, there are higher order terms here that I'm ignoring since delta lambda is very small. So if we look at this picture, the change in the coordinates from this point to this point, this is just this expression delta lambda times dx mu d lambda. So this is delta x mu. All right, and how do we interpret this mathematically? Right, this is just the components of a vector so these are the components of the vector that's delta lambda times the derivative operator d by d lambda. Okay, so now what do we obtain? Let me just ask the question. What do we obtain when we let the basis covectors act on this vector? So let dx mu act on this vector. So this is acting on the vector delta lambda times d by d lambda. And we know in this case, since this covector is the exterior derivative of a function or a set of functions, this is delta lambda partial x mu with respect to lambda. So once again, that is just delta x. All right, so the connection between dx mu and delta x mu is that dx mu gives a small change in the coordinates, but in a direction that we need to specify by giving a vector. Right? So whenever we write dx mu, it is a small change, but you have to ask yourself, a small change in which direction? And the answer is, well, in order to specify the direction, we have to give it a vector. So now I'll just return to the common practice in relativity of writing dx mu and just letting the context determine how I want to think about this, whether I think of this as a set of covectors or as a small change in the coordinates x mu. One context in which we've used symbols like this a lot is in discussing the line element. Okay, line element gives the separation between nearby points or events. For example, just to remind you, this is the line element for flat space time in Minkowski coordinates. Flat space time Minkowski coordinates. This is the line element for a two-dimensional sphere in spherical coordinates, and so on. Okay, in general, the line element is a quadratic expression in terms of the dx mu's. So if the coordinates are x mu, then ds squared is quadratic in the dx mu's, with coefficients that can depend on the coordinates, like in this example right here. Okay, so we can write the line element in general in the following form: ds squared equals some coefficient, let me call it g00, times dx0 squared, plus some coefficient g01 times dx0 dx1, plus some coefficient g10 times dx1 dx0, plus g11 dx1 squared, and so forth. All right, now we can write this more compactly as g mu nu dx mu dx nu. Okay, and remember the Einstein summation convention. We have a repeated index mu, so we're summing over mu, and also a repeated index nu, so we're summing over nu. Now if you write out all the sums, the double sum here in this expression, you'll find exactly what I have written up here. One thing you'll notice about the simple examples that I gave before are that there are no terms like this, sort of cross terms involving dt dx or dx dy or d theta d phi. But that's just because we were looking at fairly simple spaces and space-times in nice coordinates. So, for example, let's look at flat 2D space. And in terms of Cartesian coordinates x and y, let's define new coordinates alpha and beta as x equals 2 alpha plus beta and y equals alpha plus 2 beta. All right? And let's compute the line element in these coordinates. dx is 2d alpha plus d beta. dy is d alpha plus 2d beta. Then ds squared is dx squared, that's 2 alpha plus, 2d alpha plus d beta squared, plus dy squared is d alpha plus 2d beta squared. All right, so this is 4d alpha squared plus 4d alpha d beta plus d beta squared. Then from the second term we have d alpha squared plus 4d alpha d beta plus 4d beta squared. And simplifying this, we get 5d alpha squared plus 8d alpha d beta plus 5d beta squared. And we can write this in terms of our general notation as gij dxi dxj, where I'm letting x1 be alpha, x2 is beta. Okay. All right, in terms of this notation, then notice g11 is the coefficient of d alpha squared, that's 5. g22 is the coefficient of d beta squared, that's 5. And g12 and g21 are both contained in this term, so I'm going to let g12 be 4 and g21 be 4. So we always split up the cross terms in this way so that this, if you think of this as a matrix, then it's a symmetric matrix. So we give half of the 8 goes to d alpha d beta, the other half goes to d beta d alpha. So we can now write the line element for a general space-time as ds squared equals g mu nu dx mu dx nu, where these coefficients are, in general, they're functions of the coordinates, the x mu's. Now the way we've always interpreted line elements is we've viewed the dx's as really delta x mu or delta x nu. So these are small changes in coordinates between nearby points or nearby events, and then this gives the proper distance or proper time separation between those events. All right, but we now have a more sophisticated view of this symbol dx. Okay, we can view dx nu as a basis covector. So, in fact, this right-hand side can be viewed as an operator that acts on two vectors because there are two covectors here. So we can let this act on two vectors to give a number at each point in the space. Okay, now in this context, let me use the symbol, instead of using the symbol ds squared, let me just use the symbol g. Okay, g is referred to as the metric. Or sometimes referred to as the metric tensor. So the metric is an operator that acts on two vectors. We can write it this way. Let's let the two vectors be v and w. So g is expanded in this coordinate basis. It's g mu nu, dx mu, dx nu. So this operator acting on v and w. So we let one of these covectors, dx mu, act on v, and let dx nu act on w. And by the way, it doesn't matter which of these factors, dx mu or dx nu, which acts on which of these vectors, because these coefficients are always symmetric. All right, so we let one of these factors act on one of the vectors, the other factor, the other covector here act on the other vector. Now we know how these basis covectors act on the vectors. Just to remind you, we can write this vector as v, let me choose a unique index, say alpha, d by dx alpha. That's just v alpha. Then dx mu acting on d by dx alpha is just the Kronecker delta. And now in the sum over alpha, the only term that survives is the term in which alpha is equal to mu, so this is v mu. Okay, and likewise, this is w nu. Right, so when we carry out this calculation, we find this is equal to g mu nu, v mu, w nu. So again, we have an important result here. We have the very abstract notion of this operator that acts on two vectors to give a number at each point in space or space-time. But mathematically speaking, it's quite simple to construct. We just take these coefficients, the g mu nus, and wire them together with the components of the two vectors. And by wiring together, I mean making the indices repeated so that by the Einstein summation convention, there's, in this expression, there's a double sum, a sum over mu as well as a sum over nu. By the way, these coefficients, g mu nu, these are the coefficients in the expansion of this operator in the coordinate basis. These are the components of the metric. In the coordinate basis. And in later lectures, I'm sure I'll become careless and I'll refer to g mu nu as the metric, but strictly speaking, g mu nu are the components of the metric. Now observe that g, the metric, maps two vectors to a number, so it defines an inner product between vectors. Inner product. So in the case of flat Euclidean space, it's just the dot product. Let's look at a specific example. So we'll take flat Euclidean space in two dimensions with coordinates x and y, and consider the following two vectors, 2 d by dx minus d by dy, and another vector w, which is d by dx plus 3 d by dy. And let's say these vectors sit at the point P given by x equal 2, y equal 2. All right, and let's take the inner product between these two vectors. Well, thinking of this line element as a metric, this is dx squared plus dy squared. So the coefficients here, the components are just g11 is equal to 1, g22 is equal to 1. So those are the coefficients of dx squared and dy squared. And there are no cross terms here, so g12 and g21 are both 0. And for these two vectors, we can write those components. The components of v are 2 and minus 1. The components of w are 1 and 3. And so now the inner product between v and w, we can just write as gij vi wj. Now there's a double sum over I and as well as j. Now if you carry out this double sum, you'll see that it's the same thing that we obtain by thinking of this as a matrix or a linear algebra calculation. So we have v times gij written as a matrix times w. All right, so this is 2 comma minus 1. This is the identity matrix, so that's easy. Acting on 1, 3 just gives 1, 3. And now we have 2 times 1 minus 1 times 3. That's 2 minus 3 is minus 1. So the inner product between these two vectors is minus 1. Now let's carry out this same calculation, but using polar coordinates. All right, so the point P was 2 comma 2 in Cartesian coordinates, so that's a radial distance of square root of 8 at an angle of pi over 4. All right, our vector v, that was 2 d by dx minus d by dy. Let's work that out in polar coordinates. That's 2 partial r with respect to x, d by dr, plus partial theta with respect to x, d by d theta, minus partial r with respect to y, d by dr, plus partial theta with respect to y, d by d theta. Now I've worked out d by dr by dx, and d theta by dx, and so forth previously, so let me just quote the results here. Dr by dx is cosine theta. D theta by dx is minus sine theta over r. And this is sine theta d by dr plus cosine theta over r d by d theta. And all of these expressions we're going to evaluate at the point P. Okay, this is 2 cosine theta minus sine theta d by dr minus 2 sine theta over r plus cosine theta over r d by d theta. All of this evaluated at point P. All right, so at point P, cosine theta is 1 over square root of 2. Sine theta is 1 over square root of 2. So this would be 2 divided by the square root of 2, and r is square root of 8. And this is 1 over the square root of 2 times square root of 8 d by d theta. So here we have 2 minus 1 is 1. That's 1 over the square root of 2 times d by dr. And this is 3 divided by square root of 16, which is 4. That's minus 3/4 d by d theta. So this is the vector v at the point P. And we can also work out what w is at the point P. W was d by dx plus 3 d by dy. So I won't go through all that in detail, but the answer is 2 square root of 2 d by dr plus 1/2 d by d theta. Okay, now we want to take the inner product of these two vectors, and we now express them in polar coordinates. So the components are 1 over square root of 2 and minus 3/4 for v, and for w, and this is at point P, we have 2 square root of 2 and 1/2. Now the metric, well, we remember the line element is dr squared plus r squared d theta squared. So just picking off the coefficients here, we have the RR or 1, 1 coefficient is 1. The theta theta, or if you like the 2, 2 coefficient is r squared, and the cross terms vanish. Okay, so we can write this as a matrix, and at point P, this is just 1, 0, 0 r squared at point P. R squared is 8. Okay, so now if I take the inner product, I could write that as VI Gij Wj. And again, these sums over I and j can be converted into just linear algebra notation. Take this vector, 1 over square root of 2, comma, minus 3/4, times this matrix, 1, 0, 0, 8, times this vector, written in this case as a column vector, that's 2 square root of 2 and 1/2. Okay, so let me repeat the first factor, and then this 1 times 2 square root of 2 is just 2 times square root of 2, and 8 times 1/2 is 4. Okay, so now carrying this out, we have 1 over square root of 2 times 2 square root of 2 is just 2. And here we have minus 3/4 times 4, that's minus 3. So the answer for the dot product is minus 1. And of course, that's the same answer we obtained in Cartesian coordinates. So it doesn't matter, of course, which coordinate system we use. The inner product determined by the metric operator between the two vectors is the same. In this case, it's minus 1. So the metric is an operator that acts on two vectors, so it has two slots in which we can insert vectors. Now what happens if we insert a vector in one of the slots but leave the other slot unfilled? So let's say we insert this slot with the vector v. What we're left with is an operator that can still accept a vector. It acts on a vector to be put into this slot and produces a number. And we know what to call such an operator. We call it a covector. So this is a covector. It acts on a vector that we put in here and produces a number. Let's see how this works out in terms of coordinates. So g is the components g mu nu, dx mu, dx nu. And we're letting this act on a vector in one of the slots and leaving the other slot unfilled. And it doesn't matter which of these factors, dx mu or dx nu, acts on this vector because this is symmetric. So this is g mu nu dx mu dx nu acting on v. And now remember, dx mu acting on v just gives the components of v. Right, so this is equal to g mu nu times v nu dx mu. Now this is indeed a covector. It's written as a linear combination of basis covectors. And the coefficients here are the components of the covector. So these are the components of the covector that we denoted above as G blank comma V. This construction occurs so frequently in general relativity that we're going to give a special name to these components. We're going to call them V subscript mu. So we can now write this covector as V sub mu dx mu. Now you'll notice this definition of the components of the covector. Let me write it out explicitly. It's V subscript mu equals G mu nu V superscript nu. So what we have is, on the right hand side, the V superscript mu. These are the components of a vector V, and on the left hand side we have the components of a covector, and if you like we can call that covector G blank comma V. But the curious thing here is we of course use the same base letter V for this covector as we use for the vector V over here, whose components are written here. In terms of components, there's no cause for confusion. We can always distinguish between the components of the covector and the components of the vector by the placement of the indices. For a covector, the index is always a subscript. For a vector, the index is always a superscript. All right, but what this is telling us is that given any vector, we have a naturally associated covector, and the association is given to us by the metric. And because this association is so natural and occurs so frequently in relativity, we go ahead and give the covector the same base letter, in this case V, as we do the vector. This process of associating a covector with a vector using the metric is sometimes called lowering the index. So the construction of a covector from a vector using, of course, the metric is loosely called lowering the index. And that phrase just comes from the fact that we've taken a vector whose components are written with a superscript, and we've produced a covector whose index is always written as a subscript. So the index has been lowered. Now let's turn this construction around. So given a covector, say W with components W sub mu, is there an associated vector? So what we're asking is, given W subscript mu, can we solve this equation for W superscript mu, which would be the components of the associated vector? All right, and the answer is yes. We just need to invert this G mu nu and multiply by the inverse. So let's think of this as a linear algebra problem. So W mu we can write as W sub 0, W sub 1, and so forth as a column vector. G mu nu we can write as a matrix So we have G00 in the upper left, G01 and G10 in the first row and column, and then this is W superscript 0, 1, and so forth. All right, so if you work out the sum over nu and write out each of these terms for W sub 0, W sub 1, W2, and so forth, you'll find exactly the same thing as you obtained by this linear algebra operation. So we just need to multiply through by the inverse of this matrix. All right, so let's denote the inverse of the matrix that is the components of the metric, as G inverse mu nu. So this is the inverse of G lower mu nu. So in other words, G inverse mu nu G nu alpha is the identity matrix. That's the Kronecker delta alpha mu. So here we're summing over nu, and that represents the process of matrix multiplication. And we can also, of course, turn this around and write G mu nu G inverse nu alpha. And multiplying that out, we get the identity, Kronecker delta mu alpha. All right, so returning to our expression here, we just multiply through by the inverse of G. We have G inverse, say, alpha mu W mu equals G inverse alpha mu G mu nu W nu. And now this is the Kronecker delta. So that's delta alpha nu W nu. And we know the same reasoning we've seen before. There's a sum over nu. So the only, but because most of these terms are 0, the only term that survives is the one in which nu is equal to alpha. So this is just W alpha. So our result is W superscript alpha equals G inverse alpha mu W subscript mu. So given a covector with components W subscript mu, we can produce a vector and that vector has components W superscript mu given by this expression. This process of producing a vector given a covector is sometimes loosely referred to as raising the index. Now the inverse of the metric components G inverse alpha mu occur so frequently that we usually simplify the notation and drop the -1 symbol. So we let G upper script mu nu be the inverse of the metric components G lower mu nu, and it's the inverse in the matrix sense. Okay, so we can always distinguish between the inverse and the metric components themselves by the placement of the indices. So the metric itself has components with subscript indices, and its inverse has superscript indices. Right? Now, given this notation, the relationship between vectors and covectors determined by the metric is just given by V mu equals G mu nu V nu, or W mu equals G upper script mu nu W nu. So that's actually the inverse metric, and this is the metric itself.